Hello, thank you for tuning into this talk. My name is Felix. I'm just starting my third year of PhD studies at the University of York. In the paper that I've submitted to this doctoral program, we're looking at learning to choose good SAT encodings for Pseudo-Boolean and integer sum constraints. And this is work I've done jointly with Peter Nightingale and James Walker. In this talk, I'll begin by giving some motivation and background to our work. I will then briefly illustrate the idea of encoding a constraint into a SAT formula by working through a simple example. Then we'll look at how we've used machine learning techniques to predict good encoding choices. And then I will present a summary of our results and some of our findings, and finally attempt to answer any questions you might have. So why translate a CSP into SAT? To put it simply, it works very well for many constraint satisfaction problems. The tables in this slide show recent CSP solving competition results, and the top positions are taken by solvers which make use of SAT solving either in part or entirely. SAT solvers themselves are also becoming more powerful all the time. This plot shows the performance of the winning solvers in the SAT competition over the last 2 decades, and they've all been run on the latest benchmarks. So by encoding CSPs to SAT, we automatically gain from these performance developments. Now, in this paper, we are looking at encoding constraints into SAT. And so just to sort of give a flavor of how that could work, I'll give you an example, the generalized totalizer encoding. Here is our pseudo-Boolean constraint. The weights, in this case, are 2, 2, 3, 5, and so on, and x1 through to x8 are our Boolean variables. Now, in the totalizer tree structure, every term is given a leaf node, and you can see they are annotated with the weights of the corresponding terms. And what happens is, as you go up the tree, a node variable is turned on or is set to true if that particular sum has been achieved. So, for example, here, if J3 has been turned on, then E3 would be set to true as well. And this is achieved by this set of clauses, the row 10, that says for every sum in a node, the corresponding, the variable of the corresponding sum should be set to true in the parent node 2. Row 9 works on combinations. So, for instance, here, if E3 and E5 were both turned on, then B8 in the parent node would also be set to true. Notice that because our top limit is 7, we don't bother recording any sums beyond 8, because once we get to 8, we are bust. So, for example, here, 4 plus 6 would make 10, but actually we would just turn on the G8 variable because that shows that we are bust. And the clinching clause is this one, which sits at the top of the tree, and basically that's the one that we do not want to set to true, because otherwise it means we have gone bust. So that encoding is just one example. There are lots of others, and encodings have different properties that we're interested in. So a small size could be desirable, but also the propagation properties might be interesting. In this paper, there are 4 state-of-the-art encodings described and tested. And in the highlighted rows, we can see, for example, that the MDD encoding uses 2,100 variables and 21,000 clauses, whereas the GSWC uses 3 times as many variables and clauses. But when it comes to running times, the average column talks about the mean time taken to solve those problems. This one is actually 3 seconds faster in the mean time. So it's not a trivial choice. All the 4 encodings shown on the previous slide are implemented in Savile Row, as well as an extra encoding just called tree. And that gives us 5 choices for how to encode PBs. It turns out that sums can also be encoded as a pseudo-Boolean constraint with some extra at most 1 constraints. So altogether, that means we can set up 25 configurations. We ran on our cluster, we ran each instance with each of the 25 configurations, and we did it 5 times to average out any variation due to randomness in the SAT solvers. In terms of the problems that we used a corpus from a recent Savile Row paper shown below here. One advantage was that the models were already written in Essence Prime, and also it had a wide variety of problem classes Although one issue you'll spot is that there are many more instances in some of the problem classes than in others, which might have as few as one. We tried a variety of ML setups, including various regressors and classifiers from the scikit-learn toolkit, and what we found to work best was actually inspired by Autofolio, which is cited here, and that was to train a classifier on pairs of configurations, and then each classifier would then predict between those two configurations, and effectively that would give us a ranking. To make this pairwise training feasible, we needed to reduce the number of combinations that we work with. We considered portfolios of all possible sizes, and we built up a portfolio by greedily adding in the configuration which would most reduce the overall virtual best time. And we can see that even with a portfolio of size 2, we can in theory get within 72% of the overall best. In the end, we went for a size 5, and that allows us to get within 15% of what's possible with all 25 combinations. For our features, we began with 95 generic instant features that came from this paper here. And we got those by outputting flatsing from Savile Row and then running the fuzzen to feet tool to give us our feature vector. We then attempted to extract the same features from Savile Row from its internal representation just before encoding to SAT. And we introduced some new features that were specifically related to pseudo-Boolean constraints. Finally, we combined these last two sets to give us a large combined feature set. In order to create our training and test sets, we used two approaches. One was just a basic random sample to get our test set, which is the bottom row here. But the other approach was to keep together all instances of a particular class. So in other words, we were predicting on unseen problem classes, and that's the top row there. In order to evaluate this, we worked out the virtual best time as well as the virtual worst time. We worked out the single best configuration time and the default, which is tree in Savile Row's case. And we've shown here the ratio to the very best. So 1.62 means we're 1.62 times slower when we predict using the combi feature set compared to the virtual best time available. The same results are shown graphically on this next slide. And so when we split by instance, this is the virtual best at the bottom here, and this is the default, Savile Row default, and this is the single best in light green. So we can see that all the feature sets enable us to beat the single best when we were doing it by instance. But when we were looking at unseen problem classes, it was only the dedicated PB feature set that allowed us to beat the single best, and even that just by a little. So we think that what is happening is that when we split by instance, essentially the classifiers are recognizing problem classes. But when we split by class, those generic features are no use anymore. So the ones that just look at what's happening with the PBs are the ones that give us a bit of success. So in summary, we've seen that this ML setup can give us some good predictions and outperform the single best. We noticed that it's more important to choose well for the actual pseudo-Boolean constraint in a model rather than where a PB has been used to represent a sum. And also the new features that were introduced, it's nice to see that they were better when it came to predicting on unseen problem classes. In the future, we hope to extend our work to a bigger set of problems, maybe look at other encoding to SAT, other constraints, not just PBs. The 4 encodings that I showed you earlier from the table, they are actually very good when there are also at most one constraints happening in the problem instance, and so it might be interesting to put that into our features and see what effect that has. And finally, I'm sure a discussion of which features are most discriminating might also be of interest.